Good morning, class. In this video, I wanted to talk a little bit about the radian measurement as we review our trigonometric functions in this online module. And before we get into that, just wanted to wish you all a nice Easter break. Looking forward to seeing you next week when we return, and we will get more into Chapter 8. But in the first two sections, my goal is for you guys to spend some time reading it and to get into the homework, but to really review everything about trigonometric functions. It's a deep subject, a lot of information. I put a lot of videos about the trig functions themselves, so if you're interested in kind of the fundamentals of sine and cosine based on the mathematical definition using the unit circle, we won't get into that here, but there's a few videos on that, as well as SOHCAHTOA, the more common definition, both of which you can find in section 2. I'll also get into a little bit more about the unit circle, terminology such as terminal point, pi, and all that stuff, as well as getting into graphs and evaluating. So in these videos, I wanted you to have resources. Some of you probably don't need to watch them all, but whatever things you're a little fuzzy on, I wanted to give you lots of links to my lecture series on trigonometry. But before we get into that, I wanted to just briefly talk about the radian measure, as well as kind of the fundamentals of the unit circle. And in the start of the module, you'll notice I posted a calc and trig cheat sheet per se, but essentially it's just a formula sheet that I have created over the years, and I've found it really helpful, especially in calculus, just having a lot of the fundamentals from trigonometry, as well as a lot of the fundamentals from calculus. So on the in this chapter, we want to focus kind of on trigonometry, more so on the left side. But in this video, I want to talk just a little bit about the unit circle itself. What's the deal with all of the fractions of pi, as well as the relationship between degrees and the circle equation itself. And I'll leave the rest up to review in the other videos. But in the module, I've talked a little bit about the unit circle equation. You know, we just have an equation of a circle with radius 1 centered at the origin. It's pretty much the simplest circle we can create mathematically speaking. The reason it's so important is just because our fundamental trigonometric functions are defined based on the unit circle. They can also be defined by right triangles, but essentially it's always a correspondence between an angle and either two sides of a triangle or a position on the unit circle. So just looking a little bit about the unit circle, that what I would like to say is this one's filled in. It has a lot of what we call special points, a lot of the kind of critical value evaluations, such as 30 degrees, 40 degrees, 45 degrees, and 60 degrees, things that we use our trigonometric functions for sine and cosine and so forth for. But essentially, on the unit circle, the x value is the cosine of the angle, and the y value is the sine value of the angle. And that also can correspond to triangles of any size by kind of magnifying those values. So in the videos, I will get a lot more into all of those nitty-gritty details, but what's this video I want to focus on is the correspondence between angles in both degree and in what we call radian measure. So radian measure is related to distance, but it's not a distance. It's actually related back to the angle. Like an angle is not a measurable distance. Like you can't get out a ruler and measure an angle, of course. But like 30 degrees corresponds to sort of the spread of how big the kind of the arc is. I'm having a hard time kind of explaining an angle. But a radian measure corresponds to the unit circle precisely, because on the unit circle, pi over 6 represents the distance from the start, and also what we call the initial point on the unit circle is the positive x-axis at this point 1, 0. And what I kind of imagine is moving around the axis, moving around the unit circle as kind of its own axis. And if we start at 0, pi over 6 represents the literal physical distance to get there. And circles involve pi with their circumference. And that's the fundamental reason why pi over 6 is this first value here. And I think the most critical thing to remember about the relationship between radians and degrees is another formula that I have in our module module for today, which is that 360 degrees is equal to 2 pi radians. So let's talk a little bit about why that is. So in this animated image here, let's see, is this going to actually play? There we go. It'll kind of illustrate how if we have a circle with a radius value of 1, or even just r in general, but if we assume it is 1, we can kind of imagine that as being a particular distance around the unit circle. And we would call this angle 1 radian because it corresponds to 1 unit of the radius. And if we move around, you can see, kind of visualize what 3 radians is. And to get halfway around the circle, it would take pi radians, or about 3.14 units of distance to progress around there. To do the full circle, it would be 2 pi radians, and that's why we have 2 pi radians makes 1 full circle. Now, in degree measurement, a definition of degree measurement is that to complete a full rotation or a full circle, we get 360 degrees. So let me write this as an equation. A lot of times we might write 2 pi rad or 2 pi radians equal 360 degrees, but it's actually not even necessary to write the units on radians usually, because again, while sometimes we might think of a numerical value as distance, kind of my point in all of this is while technically this is 2 pi in distance or the circumference, it's really corresponding back to the interior angle, where if we're thinking about spinning around in circles, if we do 1 full circle, that would be 360 degrees, but that's the same in radian measurement as 2 pi. Because again, radians are defined as the distance around the unit circle corresponding to that angle. And I know I didn't talk about, okay, well, why is 2 pi the circumference of the unit circle? But that's even a little, well, actually, let me just write it over here. That's even a little simpler because the circumference of any circle is 2 pi r, and the unit circle by definition has radius 1. So of course, 2 pi times 1 gives us 2 pi. But anyways, that's kind of why. Now, I don't know if you've also wondered, well, what's so special about 360? Who invented that? And is there any special significance to that number? And so how I think of it is not exactly, but as far as I think most people can tell, or I haven't really looked into the historical evidence of this, but 360 days was an initial approximation by early man for the number of days in a year, as we were studying the cycle or the pattern of the sun across the year. Early humans used 360 as that kind of cycle. And if you think about the rotation about a circle, we can kind of imagine that map as kind of, rotations also involve cyclic motion. And as we study trigonometry a little bit more, I think we'll start to see a little bit more about the connection between the Earth cycle, as well as thinking about circles and triangles. But anyways, as far as I can tell, I think that's where it comes from. Is, it's also, a side note, 360 is also a very nicely divisible number. It's divisible by 2, 3, 5, 10, of course, 6, and I'm sure there's more I'm forgetting, but the divisibility of 360 is also kind of nice as well. And a lot of early societies used mathematical systems that were in base 60 or base 20 or kind of variants of 360 that kind of explained why that number made a little bit more sense historically speaking. But it's very commonplace. I think most people understand rotations with the degree measure. But my point is, if we're thinking a little bit more specifically about raw physical amounts, 2 pi is equal to 360 because it represents 1 full rotation, 1 full circle. And again, a radian measure just is connecting back to a circle of radius 1. And it's important to understand both in math, because one thing about the weakness of the degree measure is it has an implied units. It's not a mathematical number. So in equations, it's kind of like a percentage. If you use degrees in an equation, you're kind of altering its value. But with radians, we don't have that problem. We can just use radian values within equations without having to worry about how the units may affect those equations. But anyways, let's move on, because the principal thing I wanted to get into in this video is how do we convert from one to the other? So, and in the unit circle, how do we understand, pi over 6, 30 degrees, why are those the same? Well, again, back to this equation, like any sort of unit definition, like say we define 12 inches as 1 foot and we want to convert back and forth, you can treat it as an equation and solve for one or the other. So say we wanted to solve for 1 degree, well, we could divide by 360. That would give us 2 pi over 360, which would reduce down to pi over 180. So one way you can think about this is 1 degree is equal to pi over 60 radians. So say, for example, we had 32 degrees and we wanted to know what is that in radians. Well, we could just multiply both sides of the equation by 32. But essentially, to convert this into radians, we could take 32 degrees and multiply by pi over 180. And this would, let's actually remove our units from here, because this will essentially cancel out the degrees per se. You could think of that as being in the denominator, but again, I'm not going to worry about the dimensional analysis here because that's not the point of the video. But from here, again, we could reduce this. Let me just pop up a calculator real fast so that we can just get an approximated value of this. Because with pi, we know pi is an irrational value approximated by 3.14. But if we want to be fairly precise about this, let's just round it to the nearest 3 sig figs. So we'd have about 0.559. And again, we could write this in radians just to be specific about what it is, because a numerical value, right? Radians implies that this is an angle, of course, which degrees are. And if we think about, specifically any angle, we can convert it into radians. We could also do the opposite. Say we had a radian measure, like say, for example, we have 7 pi over 4, and we want to know why is that 315 degrees. So let me erase all this and let's kind of go back to, because to me, how I memorize this is not by the conversion factor itself, but just by starting with the fundamental relationship that 2 pi is 360. And if I want to solve for radians, well, I could divide both sides by 2 pi. 2 pi. And so I'd have 1 radian is equal to 180 over pi. So notice it's the same ratio, just the reciprocal. So whether you multiply by pi over 180 or 180 over pi, that's the only difference in this conversion relationship. And so, this would be the value in degrees of 1 radian. And say we had, 2.7 radians. Or actually, I guess the example I was saying was, say 7 pi over 4. We can do both of those. Again, we don't need to write the radians, but let's just be more specific about where we're starting here. And let me make that a little cleaner because that's a bit messy. Okay. I have not used my virtual whiteboard for quite some time. That's okay. So we'd have 2.7 times 180 over pi. And similarly, we could do 7 pi over 4 times 180 over pi. And with the first one, what I would probably do is just give an estimate here because it's already a decimal and we can just kind of keep it in the numerical context, which is the starting point. But we'd get a value of the angle of about 154 degrees. And I guess we'll round that to the nearest tenth. You can just use your best judgment, but we're in the range of about 150 degrees. And also thinking about the kind of common sense of this, kind of remembering, well, it takes pi radians to go halfway around the unit circle. So 2.7 radians is going to be a little short. So if I'm thinking in degrees, it would take 180 to do a half rotation. And so 150 makes sense. It's a little bit past 150 degrees, 5 pi over 6. And also thinking about some of these other angles, again, basically these are just equivalent. So the unit circle, when it's filled in like this, is nice because it gives us all of our fundamental angles in increments of 15 and 30, both in their degree form, a little easier to parse for the average person, as well as the value in the radians as well. But, if we think about being a little bit more precise about this conversion, say 7 pi over 4, we can see why this is exact. But, of course, the pi's would cancel. 180, again, is very nicely divisible. That would leave us with 45. So we'd have 7 times 45. which is, well, I'm going to cheat a little bit and just say, well, that's what, of course, 315 is in this relationship. So summarizing, the unit circle is an important thing to understand. There's a relationship between these two numbers. They're the same, just in a different form or representation, degrees and radians. And then the points themselves are points that are outlined by the circle equation. So any of these points, when we square them and add them up, they have to produce 1. And essentially the relationship between the angle and the corresponding location are what trigonometric functions are all about. And as I said at the start of the video, cosine is this, sine is this. There's a lot of other ways to do that, like with our right triangle based definition. So we can take kind of the fundamentals of how trigonometric functions work and use them to solve properties of right triangles using SOHCAHTOA. So we'll get into that in later videos. Have a nice rest of your morning and see you all next time.